Have you ever stopped and wondered what actually happens when you run a piece of JavaScript? I mean, we write the code, it runs, but what's going on inside that black box? Well, today we're going to pry that box open. We're diving into an incredible from-scratch project that shows us exactly what's under the hood.
All right, so here's our game plan. We're going to explore the architecture of Just, which is this experimental JavaScript engine built in Rust. First, we'll cover what it is, then we'll look at the 3 totally different ways it can execute your code. After that, we'll see why all that complexity matters, and finally, we'll check in on where the project stands today.
Okay, so first things first, let's get a really clear picture of what this project is all about. At its core, Just is an amazing educational tool. It's a full-blown JavaScript engine, aiming for the ES6 standard, but here's the cool part. It's built from scratch in Rust. The point isn't to go up against the engine in your browser, but to really dig in and explore how an engine like that can even be built in the first place. And let me tell you, this is a serious piece of engineering. The engine grabs your code, it analyzes it, and then it uses this whole sophisticated system of interpreters and compilers to run it. And sometimes it'll even run it in a few different ways, just to squeeze out every last drop of speed. We're going to unpack what all that means in just a minute. Now, here's where this project gets really interesting. Once your JavaScript code gets parsed into a structure the computer can actually understand, it can take one of 3 completely different journeys through the engine. So you've got these 3 execution pipelines. The first one is a straightforward interpreter. The second one uses a virtual machine to run these precompiled instructions, what we call bytecode. And the third path? That one brings in a just-in-time compiler for, maximum velocity. This tiered setup is just a fantastic way to see performance engineering evolve, all inside one project. So how do these different paths actually work? Well, it all kicks off after the engine parses your code into this tree-like structure, which is called an abstract syntax tree. Let's follow the code on its journey, from that simple tree all the way to a highly optimized machine. The first path is the tree-walking interpreter. The best way to think about this is like reading a recipe and doing each step the very moment you read it. It just walks through the code structure, the tree, and executes every instruction one by one. It's simple, it's direct, it gets everything done, but as we're about to see, it's definitely not the fastest way to do things. So the next level up in sophistication is a bytecode virtual machine. Instead of running the code structure directly, it first compiles that code into a much more efficient sort of intermediate language called bytecode. To go back to our recipe analogy, this is like translating the entire recipe into a super compact shorthand before you even start cooking. It takes a little extra time up front, but it makes the actual cooking process way, way faster.
And that brings us to the most advanced path, the real speed demon of the group, a just-in-time compiler, or JIT for short. Okay, imagine you've got this specialized kitchen robot. It watches you do a task over and over again, maybe chopping onions. After a while, it learns that task perfectly, and then it just takes over, doing it almost instantly. That's a JIT compiler. It finds the hotspots in your code and creates these hyper-optimized machine code routines to run them at incredible speeds.
Now, here's the really clever part about the JIT and JIT. It doesn't even try to do everything. It scans the code and, as the project's own docs put it, it'll bail out to the virtual machine for any operations it doesn't support. It's smart. It focuses only on what it's really good at, like number-heavy calculations, and then it just hands everything else back to the more flexible VM. It's such a pragmatic way to handle optimization, and that's a key insight right there. This all sounds, well, pretty complex, right? We've got interpreters, VMs, JIT compilers, so you have to ask yourself, is all that extra effort worth it? Let's take a look at the payoff. I mean, really, does adding a bytecode VM and a JIT compiler actually give you a performance boost that you can feel? The answer is a huge, resounding yes. This table pits the simple interpreter against the JIT-powered virtual machine. And just look at that speed-up column. For a task like calculating a Fibonacci sequence, it's almost 7 times faster. For loops, it's over 5 times faster. The performance gain isn't just noticeable, it's dramatic. So if you boil it all down to one single number, this is it. On average, across a whole bunch of different tests, the optimized paths are over 4.5 times faster. This one number brilliantly illustrates why modern JavaScript engines are so complicated. This is the real, tangible result of all that compilation and optimization work.
And to really put that Fibonacci benchmark into perspective, just look at this chart. That tall bar, that's how long this simple interpreter took. And that tiny little bar right next to it, that's the JIT. You can barely even see it. That's what a nearly 7x speedup actually looks like. It's the difference between waiting for a result and getting it instantly.
So we know it's fast, but how complete is the engine really? Since it's an academic project, it's always evolving. So let's take a quick look at what's already done and what's still on the to-do list.
And honestly, the amount of work that's already been completed is just impressive. The parser can handle most of the ES6 syntax you throw at it. The tree walking interpreter is totally feature complete, supporting modern stuff like classes and generators. Plus, there's already a ton of support for the standard library objects we all use, like math and array.
Of course, it's a work in progress. Some of the really modern features like async/await aren't in the parser yet. And some of the more advanced stuff, like classes, haven't been implemented in the faster bytecode VMs. And then there's the famously tricky evaluate function. That's also still on the roadmap. And here's what makes this project more than just an academic sketch: the rigorous testing. We're talking about over 400 tests that cover every single component, from the parser all the way to the JIT compiler. This comprehensive test suite means that, yeah, it might be a work in progress, but it's an incredibly robust and well-verified piece of software. At the end of the day, a project like Just is more than an educational tool. It's a proof of concept. It shows that with modern, safe languages like Rust, building something as insanely complex as a JavaScript engine might not be the exclusive domain of tech giants anymore. And as these tools get better and better, it really makes you wonder, could the next big high-performance browser engine come not from a massive corporation, but from a dedicated open-source community? Now that's a fascinating future to think about.